Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is Best Practices for Mineral Oil Breakdown Voltage Test. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentations, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenters today are James Graham, Senior Consulting Engineer at Weidman, and Tinku Halim, Megger Product Manager. To assist with the question and answer session, we will also have joining us Volney Naranjo, Deputy Director of Megger Technical Support Group. All right, let's get started. Thanks for joining in today, James.
Oh, you're certainly welcome. I look forward to doing this. As we talked before, I've been given a lot of seminars lately, but this is one that I have not done as often. So if I start talking about dissolved gas analysis, you'll forgive me because I have that one kind of on automatic pilot. But anyway, thanks for joining us today, everyone. Today, we're going to start off with just some high-level basics on how to take an oil sample to send to the lab for various oil quality and DGA testing. The only test they're really going to talk about today, which will come up later, is the dielectric breakdown voltage test. But this sampling procedure will work anytime you need to take a sample to send to a lab for some kind of testing and processing. Everything I'm talking about is based on this ASTM standard, D923, which has defined proper procedures for taking samples from electrical equipment. There's really not a lot to taking samples, but there's one very important point, and you will forgive me, but this will get mentioned probably several times in my next 30 minutes. And that is, you should only take a sample from any piece of equipment if you can reliably determine that you have a positive pressure. I have a quote from the IEEE DGA guide that explains why. Basically, this, especially with transformers, if you have a vacuum and you crack it for whatever reason, you're sucking air into the transformer. And that means you're going to be introducing one or more air bubbles. And if those air bubbles start traveling up through the winding and get into a high dielectric stress area, it can cause an immediate and catastrophic failure of your transformer. So you never ever want to take a sample if the pressure is negative, if it's under vacuum. If it's 0 or positive, it's generally okay, but never, never, ever take a sample when your pressure is under vacuum. If you do see that you're under negative pressure and you need to take a sample, what can you do about it? Well, there's only a couple things. If you happen to have a nitrogen fill valve, then you can hook up your nitrogen supply and repressurize the gas base by adding additional nitrogen until you can get that pressure up above 0. Generally 1 to 2 pounds is sufficient. Otherwise, you have to do something to increase the volume of the oil by heating it up. You can do that by adding some temporary additional load. As the load current goes up, the transformer will heat up and the oil will expand, and perhaps you can increase the oil volume such that the gas space repressurizes to something above 0. Or you could wait until the middle of the day when the sun's beating down on it, and that'll heat up the transformer, and sometimes that's enough to, again, cause an internal temperature rise, the oil will expand, and the air pressure will then go positive so that you can crack your sample valve. One thing that some people will try to do is not recommended, and if you're under vacuum, don't open a valve, crack it to atmosphere for the same reasons I talked about earlier. If you do that, you're going to pull outside air in, and not only will you get air bubbles, but you could potentially be pulling in moisture and other contaminants that might be floating around in the air inside your transformer, and you definitely don't want to do that. So what do you do to take a sample? Well, the first thing you should do, obviously, is locate where your sample valve is. These are on transformers, they're usually close to the bottom of the tank. They can be on any of the four sides. Quite often they're close to where the control cabinet is, but do a quick walk around and find out where the sample valves look like. If you look at the picture here, you can see what a typical sample valve will look like. Before you do anything else, then you need to put some kind of a catch basin underneath, because you're going to be pulling some oil out, and you don't want to be spilling that onto your foundation or onto the ground. That's generally an environmental hazard, and it's something to be avoided. The next step is take the plug off of the valve. You can see here in the picture that our sampling model has taken that plug off, and then you open the valve. And well, before you open a valve, you want to wipe the threads and clean. So a lot of times there'll be dirt and other debris can get trapped in those threads. So take a lint-free cloth, wipe that out real good to get as much of the solid contaminant as you can out of there, so that portion of the valve is clean. Then crack the valve, and you want to flush the valve. And typically we recommend anywhere from 1 liter to 3 liters of whatever your insulating liquid is. Flush that through there so that it'll get any remaining small dust particles, solid particles, and whatnot out of there. The volume of the valve cavity itself is generally about 700 milliliters. So you want to at least do that much to clear anything out in the valve body. After you've removed the plug and you've flushed and cleaned the valve, then if you're going to use an adapter device to attach your tubing, go ahead and connect that adapter. You can see this is a sampling device that Weidman offers that plugs in. And that can be temporary or can be left permanently in place. But whatever device you use, once it's installed, then again, you want to crack the valve and you want to flush that as well by at least 1 volume of whatever the cavity volume is for the device. You want to check as you're flushing it. You want to make sure that your whatever fluid is should be clear and there shouldn't be any visible particles in the oil. Once you've flushed the main sample valve, then if you don't want to use an adapter device, reinsert the plug and tighten that down, and then you can open up the sample port, which is the brass here on the side. If you're going to use a sample port, again, you want to crack that open and flush a little oil through that, make sure that the sample port is cleaned off. I will mention that sometimes people will not take that main plug off. They'll just open the sample port and try and flush the valve doing that. We don't recommend that practice because the oil flow tends not to clear out the entire valve cavity when you do that. It's much better to flush the valve cavity itself through the main large diameter plug, and then recap it, and then open up your sample valve. So that's our recommendation for that. Flush the sample valve after you've flushed the main valve. There's 2 types of samples that you're typically going to take when you're going to be sending these in for testing and analysis. The first sample we'll talk about is a syringe sample. The samples in syringes are basically used for DGA analysis, and there's some other specialty tests like a methanol test, which is a test you can use. Methanol is a byproduct of insulation breakdown, so it's a test you can do to assess your solid insulation condition. Those 2 require syringe samples. Bottle samples are generally for all the other tests, your power factor, moisture level, dielectric breakdown, and your other oil qualities like interfacial tension and acid number. Those all come from a bottle sample. And it has to do with the purity of the sample that you need and the volume of liquid that you need to perform the specific tests. So after you've attached your tubing and you've got your syringe hooked up, the first thing you're going to want to do is close the stopcock on that thing and then flush the tube out. You want to make sure your tubing has got all the air flushed out of it, and again, make sure it's good and clean before you take your actual sample. The closed position is as position 1. You can see a typical stopcock has 3 positions there. So position 1 closes off the syringe. Position 2 separates the syringe and allows you to flush the tubing, and position 3 is the one that actually allows you to fill the syringe. So you put your stopcock in position 2 and you flush the syringe. And again, what you're doing is you're filling it up and then draining it. So in this case, you fill it up past the demarcation point, and that's just a fancy term that says the volume marker on the side of the syringe. You want to fill it up at least that far. Once you do that, and then you switch it over to position 3 and expel all of the air and all of the oil that you just filled it up. And you need to do that at least once. If the oil still looks a little murky, you might want to do it a second time. Make sure at this point that if you introduce any air bubbles while you're filling that syringe to flush it, make sure that all those air bubbles are purged and are flushed out with the oil. You don't want any contaminant air in your syringe when you take your actual sample. Once you've done all that, then it's time to take your sample. Now you'll open the stopcock slowly again to position 2. And you want to do it slowly because that minimizes the chance that you introduce a rush of oil coming in and turbulence, which can introduce unwanted air bubbles. You watch that fill quite slowly, and once it's up to the volume marker, then you can close the stopcock to stop the flow, which again is position 1. At that point, you can disconnect that syringe and prepare it for boxing it up and shipping it. For bottle samples, it's a lot simpler procedure. It's a good idea to flush the tubing again, but it may not be necessarily, depending on how quickly you can make the transition. But you want to rinse the bottle out. And you do that, but what we recommend is you want to fill it up, and not all the way, just maybe a couple inches into the bottom of it. Put a little oil in there, swirl it around real good, and dump it out into your catch basin. Do that a couple, 3 times. Make sure that there's no debris in there, no visible water bubbles or anything like that. If you do this procedure, you'll generally be assured that you've got a clean bottle to take your sample. Then it's time to fill the sample bottle up. You do this, we recommend to insert the tube. Don't just stick it in the bottle. Push it all the way down to the bottom so that sample tubing is resting on the bottom of it. And then hold the container upright and hold the tubing such that as the oil goes in, that you're not, again, causing turbulence and bubbling. As you don't want it to be splashing around. You want it to be a nice, smooth, even flow. You want to fill it all the way up to almost the top. We recommend at least to the bottom of the neck threads. If you want to put a little bit more in, that's fine. And then what you're doing now as you fill from the bottom up, you're pushing the oil out of the bottle as it fills. And so the only portion of the oil that's actually exposed to air is that top surface layer. The bulk of the oil is not exposed to air. So that helps maximize the purity of the sample that you're going to taking. Because you always want to make sure that your sample is representative of what's in your operating transformer. And you're not just testing the bottle itself. You want to actually be testing oil that's in the same condition as the oil that's inside your transformer. So you fill it all the way up to the neck threads, and then you remove the tube and then cap it as quickly as you can. And make sure that the cap is clean too. So sometimes it's a good idea to dab a little bit of oil in there and swirl it around and clean that out too. But make sure everything's good, clean, and dry before you start filling. And then tighten that cap down. You are actually the first tester as the sample taker. So as you're filling your syringe and as you fill your bottle, take a look at the oil as it's coming out. It should be relatively clear. If it's mineral oil, it might have a slight yellowish tinge to it. If it's a natural ester like an FR3 type thing, it may have a greenish tint to it. But check it, regardless of what kind of fluid you have. It should be light colored, and it should be clear. There shouldn't be any bubbles in it, and there shouldn't be any solid debris or carbon particles or any other foreign materials. You can see a picture of a sample here. This came from a transformer that did have carbon particles and sludge inside the transformer that was pulled out as part of the sample. So this is an indication that the actual oil quality of this piece of equipment was not in the pristine condition. It was not in good condition. But you're the first test when you pull that sample, because you're the first one that can look and see what the oil looks like. Do know that if it comes out too dark or if there's too much contaminant in it, most labs won't be able to do many of the tests that you may be asking for, because if it's too gunked up, it will wreck the sensors on the test equipment. It'll force them to have to shut down that equipment and spend a fair amount of time flushing out the equipment, cleaning out all the debris that was picked up from that bad sample, and then they have to redo their calibration checks before they can go back to productive testing again. And so oftentimes, if the oil is in really bad shape, if it's jet black, clearly this oil's been heavily overheated, you may get a call from the lab saying, we can't test your sample because of the quality that we got. So be aware that if it's really bad, you might want to call the lab before you send it in and say, this is what it looks like. Can you do anything with it before you send that sample in? As you may guess, if you haven't already figured it out, keeping that bottle as clean as possible is critical. You want to make sure before you start that the bottle is dry, that there's no moisture left in it. You want to make sure there's no solid particulates in it, such as dirt or carbon particles or any solid contaminant. You want to make sure it's absolutely clean. You want to make sure there's no foreign things in there. In this case, we have gotten samples that have moths and used cigarette butts that were in the bottle, and they just filled it up oblivious to what they were doing to their oil sample and sent it into the lab. So you want to make sure that bottle is not only dry, but very clean before you take the sample. Otherwise, the results you get from your tests are not going to be representative of what's inside your transformer, and you've basically wasted some time and money. The test results can only be as good as the purity of the sample taken. So if you give us a contaminated sample, you're not going to get real accurate test results. It will be accurate in the sense of that's the quality of the oil as tested, but it will not be accurate in the sense of this is the condition of the oil that's inside your transformer, and after all, that is what you're most interested in. Once you've prepared your samples, once you've taken your samples, then you want to prepare them for shipping. So the first step is for each bottle or syringe that you filled out, you want to put a label on it and identify what transformer or piece of equipment it came from. So typically you'll have a customer ID if that's important to you, but definitely you want to put down the serial number of that transformer and maybe the location if you're doing multiple sites in a common shipment. This is so that we know which sample came from which piece of equipment that you want to test. You should also at this time fill out your sample request form that has that same identifying information on it, along with selecting what tests you want performed, any notes that you want to advise us from, any comments that you want to make. You want to have the address and the contact information of who the sample results should be sent to. You want to give us equipment ratings, because for oil quality, equipment ratings are important. So we want to know, for example, if it's a transformer, we like to know what the KV rating is. And although we don't really need the KVA rating, it is handy information to have if we want to explain some anomalous readings. Some smaller transformers have sometimes slightly different gassing patterns than larger power transformers do, for example. So it's a good idea to put that down. Also, the new DGA guide actually needs to know what the year of manufacture of the transformer is so we can calculate its chronological age. And so be sure when you fill out your sample forms that you're adding that year of manufacture in if you can. Make an effort to fill it out. All of us in the industry recognize that some older transformers, they do not have a year of manufacture stamped on the nameplate. And depending on what kind of transformer owner user you are, you may or may not have good records of when that transformer was purchased. So you may not always be able to identify that year of manufacture, but do make an effort to do that, because it does help us interpret, especially your DGA information, a little more accurately than if we don't know what that transformer year of manufacture is. So all that information goes on the sample request form. A lot of that same information will be on the label, depending on what type of label you use. Once you've got everything labeled, then place your sample container into an opaque shipping carton and seal it. And the idea here is you don't want to expose your samples to direct sunlight, ultraviolet light, or extreme heat. If you do that, it will cause the oil to react. Extreme heat will cause it, in some cases, to start producing the heating gases, so you'll have more fault gas than actually had present in your transformer oil from the tank itself. So you want to keep that minimized. Don't take your bottle and your syringe and set it on the dashboard of your truck while you go off to lunch or go take some more samples. Don't let it sit in the sunlight. That will cause that oil to start breaking down. You want to keep it cool for the same reason. So put it in an opaque container and seal it up. Store it in as cool a place as you can. If you're going to keep it in your truck, you might want to put it in the toolbox or under the seat or in the back cab. But again, keep it out of direct sunlight so it doesn't heat up as much as possible. And then as soon as you can, ship it off to the lab of choice. Sometimes people say, well, how long can I sit on this sample before I should send it in? And the answer kind of depends on how accurate do you want your sample results to be. From DGA, our studies have shown even if your syringe has perfectly good seals and it's all functioning properly, you can still lose approximately 1% of the gases that are dissolved in that oil per week until it gets sampled. So at Weidmann, we generally would like to get that sample within 5 days of the sample having been taken. We know that some places like wind farms or solar farms, where you may have a lot of transformers on a site, that you may want your personnel to sample a bunch of transformers and then send them all in a batch. And you may not be able to do them all in a single day. Well, that's okay, but if it's going to take more than a week to get them all, then do it in separate batches. Take this first batch and send it in, and then when you get the second set done, send that in as a second batch. Try not to sit on them for 2 or 3 weeks until you can get a high volume of samples to send in all at once. Like we said, we'd like to receive it approximately 5 to 6 days after that sample is taken, so that we can minimize chances of mishandling of the sample. Exposure to things that might cause contamination to be produced within the sample itself. So 5 to 6 days is the lead time between sample taken to when we would like it to show up in the lab. Some sampling considerations when you're taking samples, when to take them and such. Sampling time frame just means note the time of day or the time of year that you're taking the sample. Ideally, you would like to take it at the same time of day, at the same day of the year if you're doing routine maintenance samples. And the reason for that is you'd like the fluid temperature to be as close to the same temperature as you can from sample to sample. When you do take the sample, do make an effort to determine what the temperature of the oil sample was as it was taken, and record that on your sample form so that we can include it in the information on the test report. It's not absolutely critical to know, but in some cases, if we can see a wide variation in oil temperatures, that can sometimes explain why a normal transformer looks like it's generating active gassing patterns. It could just be because as the temperature goes up, it drives more gas out of the oil. So do identify the temperature if you can. If you don't have a thermometer handy to stick in the bottle real quick to get a reading, you can always, if the transformer is in operation, you can look at the temperature gauge on the transformer and use that as the oil temperature. You want to visually inspect, again, like we said, to make sure that it's a good, clean sample. If there are contaminants floating around there that came from the inside of the tank, you want to make note of that on your sample form so the lab's aware of that. Again, double check your identification, make sure that the label on the shipping box matches the label on the sample and the sample form, so that when it comes in and we report the results go with the sample that goes with the correct piece of equipment, so that we don't get them cross-reported, if you will. So we want to make sure that we know what's going on and we get the right results with the right piece of equipment. Again, you want to make sure that all your sample containers, adapting devices, tubing, anything you use that the oil flows through on its way to taking that sample, you want to make sure it's clean and dry before you start. One last thing, you want to pay attention to the liquid levels, especially in the smaller pieces of equipment. If, a lot of the really small transformers may not have a liquid level gauge on it. But if they do, you want to make sure that you're reasonably certain that you're not pulling out enough oil to go below the minimum oil level required for proper operation of that equipment. If the oil level drops below the top of the active parts of a transformer, that can cause both dielectric and thermal problems that can lead to a rapid transformer failure. So it's something you want to avoid. We understand that some smaller transformers may not have gauges on them. You may not know what the liquid level is. You're just going to have to do what you can to ascertain that over the years you haven't taken too much samples out. Now recognize that we're only taking samples. A sample bottle is approximately 300 milliliters. A syringe is anywhere from 30 to 50 milliliters. So even with a small transformer that might only have 400 or 500 gallons, it's going to take a lot of samples before that level is going to appreciably be reduced to the point where you need to start worrying about it. So unless you've been taking multiple samples per year for many, many years in your small transformers, it's probably not going to be an issue. But do be aware that if you're not certain, if you suspect that the liquid level is too low, don't take the sample until you can verify what that level is and replenish it before you take your sample. So in conclusion, whenever you take a sample, you want to make sure that you're doing it safely. And so make sure that you can safely access the sample port. Now, if it's a pad mount transformer and that sample port's inside the compartment where the cables are, follow your own, your local, state, and company safety regulations. Some companies will not allow you to open the cabinet if the transformer is energized. So if the company you work for has that rule, make sure you de-energize the transformer before you take the sample. Never open the sample under negative pressure conditions. I think I might have mentioned that once or twice already. Never open a transformer that has pressure under vacuum, because you want to avoid pulling in contaminants and especially air bubbles in. So if it's negative, don't open a valve, don't crack a fill valve to vent air. Don't do any of those things. As I said, you need to do something to repressurize it, whether adding gas or heating up the oil so the gas space gets compressed. But do not open the valve under any circumstances if you're under negative pressure. Environmental, you want to be environmentally responsible with the oil that you're pulling out. Don't just dump it on the ground and bury it. That's why you use a catch basin, put it into some kind of container, and then depending on the type of oil you have and whether or not it's PCB contaminated or not, dispose of it properly. Again, after you take your samples, make sure your sample containers are covered up and shielded from direct sunlight, and keep them as cool as you can. Don't leave them sitting out in the hot day sun while you're doing your duties. Put them someplace where they're shaded or protected from direct sunlight. And as always, make sure you're not contaminating the sample in any way. And the best way to do that is make sure that all your sampling equipment is clean and dry, no visible moisture, no visible solid particulates, and make sure you purge the airspace a couple times before you take your samples. So that's all I have on transformer sampling. This is just a short plug of some of the services that Weidmann offers that you may not be aware of. Weidmann is primarily known for producing cellulose insulation products for power transformers, but we do have an engineering services and laboratory group as well. We do offer lab testing services, and on some parts of the country, we also can offer our field technicians to come to your site and take samples for you. Our engineering services, this is the group that I work in. We do transformer condition assessments, load studies, cooling studies of transformers, and we do a lot of educational training webinars, primarily on transformer testing, DGA analysis, general oil quality testing, and those kind of things. We also offer a line of transformer monitors and gauges. If you're interested with that, you can contact me, or if you happen to know who your Weidman regional sales manager is, contact them, and they can get you information that you might be interested in. So with that, that's the end of my presentation. I'm going to turn this back over to Michael.
Thank you. Yeah, all right. We're going to throw things over to Tinku Hilem real quick. Here we go, Tinku.
Okay, well, hi everybody.
Wonderful.
Let me just put it into full screen mode. There we go. Okay, so we've got the sample successfully from the asset that we would wish to do the testing from. What I would like to cover now is the actual preparation of the test equipment that's going to test the actual oil. So this is the OTS, which is a dielectric breakdown tester. So I want to cover the vessel preparation, what we need to do in order to make sure that everything is ready and in place to test the oil. And then at the end of the presentation, I'd just like to cover some of the testing we've done within Mega itself. We've looked at environmental tests for OTS, and we've also characterized gap variation between the electrodes, just to see how that may affect any sort of breakdown results. So if we go straight into vessel preparation. So what I'd like to cover here, we're going to look at storing the vessel and how we can actually clean the vessel, how we can set the electrode gap to make sure that we have the correct gap according to the standard, to make sure that we get the expected results that we wish to get from the oil that we're testing. And then we'll look at the contact with air, how we can minimize contact with air. We need to make sure that we don't get any contamination by contact with air. And then we'll look at the stirrer options with the different standards and which is the most applicable one for the testing that is to be performed. Okay, so when we look at storing, so IEC recommends that the actual test vessel assembly is a separate test vessel assembly is used for each type of insulating fluid. So you try not to mix different types of insulating fluids. So say, for example, sample 1 would be a mineral oil, sample 2 could be an ester, sample 3 would be a silicon oil. So the recommendation is that you use a separate test vessel for the different types of insulating fluids. And it also recommends that the actual vessels are filled with a dry insulating fluid. This is to ensure that there's minimal contact with the air during the actual storage of the actual vessel. And this needs to be in a dry place, typically a cabinet, a dust-free cabinet. So that's IEC's recommendation. If we now look at ASTM's recommendation, again, the vessel can be filled with an insulating fluid. However, ASTM also suggests as an alternative that an empty vessel can be stored, which again needs to be in a dust-free cabinet. So that's the slight difference between the two standards. So when it comes to cleaning, what do we need to do? So for an empty vessel, so if you're following ASTM and you're storing your test vessels without any oil, or in fact, if you're testing a different type of oil, so for example, you were testing mineral oils and now you've moved on to silicon or ester, you need to follow a cleaning procedure in order to make sure that you've removed any sort of contamination from the cell before you start to begin testing. So the first thing is to actually clean with an appropriate solvent and then rinse with the sample fluid twice. And ASTM recommends the use of dry hydrocarbon solvents, and some of these could be kerosene. This meets ASTM D235. You can use acetone or toluene, however, not in Europe. The main thing here is to avoid any low boiling point solvents, because they evaporate quickly, and that has a cooling effect on the actual components that the solvent is in contact with. And by cooling, that could then introduce the risk of condensation. So we must avoid using any sort of low boiling point solvents, which is why ASTM recommends these three solvents that we have above. And also during any of the cleaning procedure, use only lint-free wipes to avoid any particular contamination of the vessel. Okay, so we have cleaned the cell. This example here is basically if you have a cell that has been stored with oil, or if you're testing another type of oil, you need to make sure that you drain that first completely. So you remove all of the previous sample. You then need to rinse all the internal surfaces. So you're rinsing the walls of the vessel, but you're also rinsing any part that comes in contact with the sample oil during the actual test procedure. This is the electrodes, the impeller, and the walls of the vessel. And you need to do this twice with the sample fluid that you're testing in order to make sure that you've removed any of the previous contamination. So you're just testing the sample that is under test now. Okay, and then as soon as you've done the rinsing, you need to make sure that you fill with the sample oil as quickly as possible. So immediately, you need to make sure that this is done in order to minimize any contact with air during the actual time between rinsing and filling for the actual test. ASTM-D 1816 specifies that this should typically take less than 30 seconds in order to minimize that contact with the air. And you need to make sure that you fill the vessel slowly and carefully. And in order to do this, if you fill the oil too quickly into the vessel, you'll cause turbulence within the oil, and that can then generate bubbles. So you want to try and avoid the formation of bubbles. And with the OTS vessel, you need to make sure that you fill the oil to the fill line. So here you can see the fill line is a 400 milliliter line that's clearly labeled on the test vessel. You make sure that you fill up to the fill line, not above the actual fill line, because when you place the lid on the vessel, if it's over the fill line, you'll get spoiling of oil above the top of the vessel. Okay, so another thing to bear in mind is making sure that when you do any cleaning, that you don't actually touch the electrodes. This is to avoid any sort of contamination of your electrodes. And you also need to check your electrodes for any sort of damage, any sort of pitting or scratches that may happen through the course of its life, because this will eventually cause unexpected results. So just check before you're doing your testing to make sure that there's no damage to the surface of the electrodes. And remember, cleaning doesn't apply to just the vessel walls itself. It applies to all of the parts that come into contact with the sample. So this is the impeller, the baffle plate, the lid, the electrodes. Everything needs to be cleaned and also flushed with the sample oil before you proceed with the test of that sample. Okay, so we've got a test vessel, we've cleaned it, we've got everything ready. The next thing we need to do is to check to see if the electrode gap is correctly set. You don't need to do this for every single test, but you just need to make sure that the electrode gap is set correctly before you proceed with testing for the day. Okay, and this is very important because if your electrode gap is not set correctly, then the results that you get will be invalid. So you need to make sure that this is set correctly according to the standard. And of course, avoid any movement of the electrodes. So once you've actually set the gap between the electrodes, you then need to make sure that you use the locking mechanism on the OTS vessel to actually make sure that those electrodes are locked into place before you then proceed with testing. Okay, and also, very important point, don't set the electrode gap with oil in the test vessel. Make sure that the test vessel is empty before you're actually going through the process of setting the electrode gap. And the way to do this is to hold the gap gauge with the keychain, okay? This enables a better view of how the actual gauge fits in between the electrodes. You're not obscuring the view, because if you hold the actual gauge, you're obscuring your view, but also you're introducing contamination by touching the gap gauge, which may then contaminate other parts of the vessel. By holding it with the keychain, you're also making sure that you're not forcing the gauge between the electrodes. You don't want to do that. You want to make sure that it just drops between the electrodes, and then you can make the adjustment. So you're not forcing it between the electrodes. Okay, so the gap gauge is in place. We now need to carefully adjust without over tightening. This is very important that we don't over tighten the actual electrodes. So the gap gauge should just be able to slide between the electrodes with the minimal amount of force while it is being held with the chain. So you're just placing it between the electrodes, gradually adjusting the electrode gap, and then you'll notice that there's just a very slight force when you try and move the electrode, the gap gauge, out of the way. If too much force is required, then over tightening has resulted, and you just need to make sure that you back the electrodes off and then recheck and readjust to make sure that you have the correct setting. Again, a very light force is needed to move the gauge. And then finally, remove the gap gauge. So you now know that you have the correct distance between the electrodes. And again, by removing it, there should only be a very slight sort of detectable drag between the electrodes once this is completed. And another important point to remember here is when you're actually doing this, try and avoid breathing near the vessel, because this can also introduce moisture, which is a contamination for the dielectric breakdown test. Also avoid leaning on the rim or any of the other parts of the vessel, because this could potentially cause mechanical distortion. So the proper way to do this is to hold the gap gauge as we showed previously, and try not to touch or lean on or breathe on any part of the vessel when actually doing this. Okay, and the other thing to note is that if you are going to move the portable oil tester from one location to another, just please do ensure that you recheck the electrode gap when you arrive on site, just to make sure that you're confident that the gap setting is correct and hasn't moved, and then you can proceed with your testing as planned. So the next thing we need to do is look at how we can minimize contact with air. So previously we said we need to rinse it, and then we need to fill the sample fluid immediately. And why is this important? It's important because oil is hygroscopic. Hygroscopic means that oil has the characteristic of absorbing moisture from air. It does this naturally. It's part of its chemistry to actually continuously absorb moisture from air. So we need to make sure that we avoid or minimize contact with air. And the example shown there is 30 parts per million in terms of moisture contamination in your sample can actually halve the breakdown result that you're expecting. So it's very important to make sure that we minimize contact with air. Okay, and oil is also readily absorbed on the surface. So this means when you're rinsing or when you're draining the sample, there's always a little thin film of residue of oil left from the previous sample. And that thin film of oil, if left in contact with air, will absorb water. So when you're introducing your next sample, and then you go through the process of the test with the impeller stirring the solution, you're then introducing that contamination from the thin film of oil that existed in the previous sample. So it's very important to minimize contact with air, and that's why we need to make sure that we fill with the sample immediately after rinsing. So we're minimizing that contact. Okay, and then the next thing we need to do is place the lid on the oil vessel, again, to prevent any further contamination. We also need to make sure that we allow the sample to stand for a few minutes. This is to disperse any bubbles that may have been created by pouring the oil into the test vessel. But we also need to make sure that we don't do this for too long, because it can also cause problems with the hygroscopic properties of oil, because it's always trying to absorb moisture from the air. And then the baffle plate and the lid must be fitted to prevent air contact while the oil is left to stand, as you can see there in the picture on your right. the baffle plate in place with the impeller below. And a very important note here is that the baffle plate must come in contact with the oil. So if you fill the oil to the fill line, which is the 400 ml fill line, you then place the baffle plate. It actually sits just on top of the oil. So again, it's minimizing any contact with air that may exist in the headspace. And we also need to ensure that the oil doesn't pass the upper surface of the baffle plate. And this will happen if you fill above the fill line. So make sure you fill your oil to the fill line, and then that will not cause this escape of oil through the top of the vessel. Okay, so that's contact with air. So now if we look at the different stirrers, so for IEC recommends an impeller. Typically, an impeller would be used for transformer oil because this oil is typically circulated in the asset, and that's the impeller there you can see. It also allows the use of a magnetic beam. However, this is permitted where there's no risk of removing or in any way preventing magnetic particles from being present in the actual testing sequence. And that's the magnetic beam. And also there's an option for no stir. So this would typically be used for static applications. So an oiled filled circuit breaker that isn't circulating the oil, you would then choose to have no stirring as your option. So for ASTM, so 1816, the impeller is stirring throughout the test sequence. This is for 1816, and that's the impeller. 877 does not specify all sample stirring. So 1816 stirs throughout the test sequence. 877, there is no actual stirring in that. However, what you need to be aware of is the need to make sure that the vessel preparation is done, the minimal contact with air is done, because with the stirring, you're maximizing the homogenization of the oil. So you're actually stirring the actual oil, but you could also potentially, if the sides of the vessel have been contaminated with the previous sample because of the oil being adsorbed onto the surface, which may then contain moisture, you're then stirring all of that into your specimen sample, which will then affect your breakdown results. So this is why it's key that we need to make sure that once we've rinsed the vessel, that we then need to make sure that we fill it immediately afterwards in order to avoid that. Okay, so that's the vessel preparation in a summary. So we've covered storing the vessel, cleaning, but cleaning all the parts that will come in contact with the oil sample, not just the vessel walls, but every component that comes in contact. Setting the electrode gap is key to making sure that you have the confidence that the test results will be what you're expecting them to be. And this needs to be done in an empty vessel with the gap gauges in the way that we have described. We need to minimize contact with air because oil is hygroscopic and it's readily absorbed on the surface. So it's always on the surface of all of the components that you've tested your previous sample with, and that is always trying to absorb moisture from the air. And also selecting the correct stirrer option as defined by the standards. Okay, so everything that I've discussed here is covered in our vessel preparation guide. This is a fully comprehensive guide that gives all the information that I've presented in this short presentation, and it gives a lot more information, or there's a lot more comprehensive and detailed information on vessel preparation, with the goal of eliminating the effects of moisture and contamination. Okay, so that's vessel preparation. What I'd like to do now is just to go over some of the testing we've done within Mega as a company to see how OTS performs under various conditions, so environmental conditions, but also we're looking at to see how variations in the gap between the electrodes can affect results. Okay, so we've performed two tests. The first one is the temperature coefficient investigation. So this is looking at how OTS performs where the ambient temperature changes from a low temperature up to the highest operating temperature, and also the electrode gap variation testing. So if we look at the temperature test, so this was run with an OTS 60 PV to investigate the temperature effects. The temperature range was from -10 to 50 degrees centigrade. The stated operating temperature for OTS is 0 to 50 degrees centigrade. So we were testing to see how the unit operated at low temperatures outside of the specification. So what we did for the test, we had two OTS 60 PVs. We had one in the chamber, which we call the OTS chamber, and then we had a reference OTS, which was not subjected to the environmental temperature changes. For both of these OTS, the one in the chamber and the reference, the oil was always at 20 degrees centigrade. So we were looking at the effects of ambient temperature on the actual instrument itself, but the oil remained at 20 degrees centigrade. Okay, and we did a number of tests. So when you see the graph, you'll see that one set is actually a complete ASTM D1816 test, which consists of 5 breakdowns. And this was the resulting graph from all of the testing that we did. So you can see for each of these sets, we had 5 breakdowns. So on your left axis, you can see the breakdown voltage. At the bottom, these were the temperatures that the chamber OTS was subjected to. And if you also look at the legend below, so we've got the circle is the average of all tests for the chamber OTS, and the square is the average of all tests of the reference OTS. So we wanted to see how the chamber OTS across the different temperature ranges behaved when comparing it to an OTS that's not subjected to any temperature changes. And as you can see from the graph, it follows very closely to the reference OTS. So this was a very good result for us. We were very pleased to see that there was a very little effect of temperature, and obviously outside of the specification. So at -10 degrees centigrade, we were still within the specification for the reference OTS, which was which wasn't subjected to the low temperature. So the conclusion from this is that there is no significant temperature coefficient in the OTS 60 PV. This is a very, very good result for us to see how the unit performed outside of the actual operating specification. The second test that we did was to do with gap testing. So this was again using an OTS 60 PV. Here, this was running an ASTM D1816 test, typically at 1 millimeters, but we actually changed the gap of the gauge from 0.8 millimeters, and we did it also at 1.2 millimeters, just to see how that affected the breakdown results. We really wanted to see if there was a linear relationship between the actual gap between the electrodes and the breakdown voltage that resulted from that. So we performed 10 ASTM tests per gap setting. So that's 50 breakdowns per gap setting. This gave us quite a good statistical data point to actually work from. And this graph now actually shows the averages. So if you look at the x-axis column, this is the breakdown voltage. And at the bottom, you can see the gap setting. So we had 0.8 millimeters. We had 1.2 millimeters, and then we went back to the 0.8 millimeters. And at the bottom of the legend, you can see the test 1 to test 10 showing all the average breakdown results. And as you can see with the 0.8, we were achieving typically around 25, 26 kV. When we went to the 1.2, obviously a larger gap between the electrodes, you'd expect a higher breakdown. And again, we were achieving around the 40 kV. And then back down to the 0.8, we were then achieving what we had before, which is around the 25, 26 kV. So if you look at the next graph, so this graph, what this is doing, it's actually looking at the overall average, which is the X, and the theory calculation if linear with distance. So this proves, so you can see the cross and the circle with the 0.8, with the 1.2, the cross and the circle are in the same position, and with the 1.8 again, nearly in the same position. So from this, we can say that there is a linear relationship between the electrode gap and the actual breakdown voltage. So the conclusion from this was that the breakdown, as I've just said, was shown to be approximately linear with the distance. Now, this was with the mushroom electrodes in the region of the 1 millimeter, so it went from 0.8 to 1.2. In terms of generally expressing this accounts for a plus or minus 10% change in breakdown voltage. So if you were running a ASTM D1816 test with mineral oil at 20 degrees centigrade and you were getting 33 kV, a plus or minus 0.1 millimeter change in your electrode gap would then result in plus or minus 3.3 kV in your electrode gap. So you can imagine if you turn up on site, you don't test or you don't check your electrode distance between the electrodes with your gap gauge, and it could be that it's 0.2 millimeters out, 0.3, you don't know, it could be out. That will then result in a significant change in your expected breakdown voltage. So that's why it's key to make sure that you check your electrode gap every time you move the equipment and at the beginning of the day, just to make sure that you have the confidence that everything is set up as you expect it. Okay, so that concludes the testing that we've done, and I shall now pass over to Michael.
Wonderful, thank you. So at this time, the presentation portion of the webinar is officially concluded. I will now take some time to answer as many of your questions as possible. If you have any questions, please submit them down to the Q&A box in the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo on any Megger products. As a reminder, a copy of these presentations, certificate of attendance, and a link to the video recording of this webinar will be sent to all attendees in 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars and register for our next webinar on July 7th titled PD Monitoring on Rotating Machines. All right. Let's jump into some questions. We have a lot of really good ones I'd like to get to today, the first of which I'm going to direct to Volny Naranjo. Volny, what is the recommended oil volume for breakdown tests?
Thank you, Michael. So it depends on the standard you're using. ASTM 1816 requires 400 milliliters for the test vessel. So remember, in addition to the vessel, to the actual sample that you're going to be testing, you need oil to rinse the cup, to rinse the vessel, and it depends how dirty or how contaminated it is, or how you have stored it, that you will need more oil to rinse it several times to get some good cleaning there. So I would say minimum twice the volume that you need for testing. Now for 877, you can also test with 150 milliliters. There's a vessel that we have that has that volume, so that will require less oil. But also consider that you may not get a good result. You may get something that it's not within the expected value, so you may want to have some additional oil there for the test.
Thank you, Volny. Our next question is going over to James Graham. James, in the case of a sealed transformer, do you need to vent the unit before taking the sample?
The answer to this is no. A sealed transformer does not need to be vented before you take the sample. In fact, you want to avoid venting a sealed transformer because you don't want to expose the conditions inside the tank to atmosphere, and that's to avoid pulling in moisture and other contaminants. So no, you don't need to vent the transformer before you take the sample.
All right, thanks a lot. Back over to Volny. For field oil breakdown tests, do I need to sample to a bottle, or can I sample directly to the test vessel?
Well, from the presentation, from the different recommendations, you can see that it is very important to have a very good sample. I would not recommend sampling directly to the vessel because, well, you need you need to rinse it. In that process of trying to rinse it and sample directly from the valve, you may end up introducing contamination. You are in a substation, could be windy, could be different conditions that can affect the testing. So I would not recommend testing directly to the vessel.
Thanks, Volney. So James, if the sample is taken during routine system shutdown and the transformer is negatively pressurized, how can we take a sample? Would it be using nitrogen to equalize the pressure?
Yes, as I mentioned in my presentation, you never want to take a sample if the transformer is under negative pressure, which means it's under vacuum, because when you crack open the valve, you're going to be sucking air in. And so you want to repressurize that. And so the best way and the easiest way is if you have a fill valve, hook up your nitrogen supply to that fill valve and add enough gas to bring that pressure up above 0. Typically to 1 or 2 pounds is sufficient.
Thank you, James. Back to Volney. What can be used to dry the vessel?
Okay, I guess so. The best thing is to, I guess this question is related to using some of those other fluids to clean the vessel that Tinku mentioned, like acetone or all that. So those evaporate very fast, and I guess you don't need anything to clean the vessel or to dry the vessel other than that. But if you need to do something or you want to do it, the first thing is to consider lint-free cloth or towels, so you don't introduce any particle there, any contamination. Again, we are trying to have the best condition inside the vessel for you to test and not introduce any particle that will create or cause a lower breakdown voltage.
Thank you, Volney. So over to Tinku. Could you explain cleaning and flushing procedures when using more than one insulated fluid in the same test vessel?
Okay, so if you've got mineral oil and then you wish to test another type of oil, whether it's silicon or ester, you need to make sure that you've removed any of the mineral oil residue before you then introduce the sample that you wish to test. And the way to do this is to actually put a small amount of the sample that you wish to test into your test vessel, move it around, make sure you're covering all of the areas that are inside the test vessel. You also need to make sure that you're also flushing the components, so the impeller, or if you're using a magnetic bean or the electrodes, you need to make sure that you're covering all of that and rinsing any of the previous samples residue with the new sample. And you do that a couple of times. So you put it in, mix it around a bit, drain it, and then put another flushing sample in there to make sure that you've done your best to remove the previous sample.
Thank you, Tinku. Over to James. Is the plug required always during the sampling, or can I sample directly from the valve?
You can sample directly from the valve, but the key is that if you're going to do a syringe, you're going to be using a small diameter tube. So if you're trying to use the main, the large diameter opening on the valve, you're going to need some kind of adapter to reduce the diameter down so it fits the tube. Most sample valves have a sampling port on the side that has that small diameter opening that will fit the typical size tubes that you use. So you don't need to have a special adapter to reduce it down unless your sample valve does not come equipped with the sample port on the side.
All right, thank you. Over to Tinku. I have experienced large differences in oil breakdown voltages when testing with D877 and D1816, same gap, same oil sample. Could you explain the differences in the ASTM standards pertaining to the electrode geometry and influencing factors?
Okay, I'm a little bit puzzled with this question because the actual electrode gap is different for 1816 and 877. So for 1816, it states that you can actually perform the test at 2 millimeters. However, if you don't achieve a breakdown, you then reduce the electrode gap to 1 millimeter. 877, the electrode gap is 2.54 millimeters. So they're different gap settings altogether. With 1816, that uses the mushroom electrodes, and with 877, that uses the cylindrical electrode. So that will have an effect on the actual characteristics of how the oil is broken down between the electrodes. As for geometry and influencing factors, well, the influencing factors is the difference in the difference in the distance between the electrodes and the actual different type of electrodes.
All right, thank you, Tinku.
Yeah, Michael, let me
yes.
jump in on that. Also,
Absolutely.
the D877 method of testing also has, like he said, it has the flat electrodes at a specified gap, but the oil is also stationary. In the 1816 method, you use the mushroom electrodes at either the 1 or 2 millimeter gap, but that oil is also circulating through while they apply the voltage. And
Absolutely, a very good point, James.
And because of that, IEEE no longer recognizes D877 as a valid breakdown test for oil that comes out of an operating transformer. It's still okay for if you're sampling from a bulk container, or if you're sampling from like an oil circuit breaker or a regulator, something like that. But for transformers, the 1816 method is considered to better simulate the conditions inside an operating transformer, and so it's the recommended test now.
Thanks for jumping in there. So to Volney, is it better to measure with a 1 millimeter gap or a 2 millimeter gap in the field?
Okay, from the gap values, I'm assuming this is a question related to 1816, and well, the recommendation is to start with the 2 millimeter, but if your oil does not break down, then you have to move down to the 1 millimeter. The typical voltage that the field instruments will go up to is 60 kilovolts or 70 kilovolts. So usually good oil or oil that is recently processed or it's in a transformer, you expect to be in the range of or in a very good condition. So usually what I've seen is that it doesn't break down at 2 millimeters. So pretty much kind of the standard is that you go directly to the 1 millimeter value, because that's where the voltage or the oil will break down. If you have an instrument that can go higher than 60 kilovolts, for example, there's 80 kilovolts or 100 kilovolts, you may get the oil to break down at 2 millimeters, but typical field testing is 1 millimeter.
Thank you, Volney. Back over to James. James, is there a best time of year to pull samples?
There's really not a best time of year to take samples, but what you do want to pay attention to is what are the environmental conditions. You don't want to take samples whenever you've got extreme temperatures, either hot or cold. You also, it's recommend you not take samples if you've got heavy precipitation in the air. So if it's raining, snowing, sleeting, or if you've got really heavy fog, because when you take your bottle sample, it's going to be absorbing some moisture while you're filling the bottle. So on that basis, you want to take the time of year when you have the best weather, I think is probably the right answer for that. The actual temperature of the oil isn't all that critical. We do like you to record it for us. The reason we say that the similar types of year is just it minimizes the chances that the oil temperature will be approximately the same temperature. So if you forget to record it, we can make some assumptions on what that oil temperature was. So as long as the weather conditions are fairly good, it really doesn't matter whether it's a summer, fall, spring, or winter time when you do that. But do try to take it the same time of year every year.
All right, thanks, James. Tinku, the oil breakdown test results show a pass or valid, but the result is low compared to the expected result. why do I get a pass?
Yeah, I've seen this before. I'm trying to rack my brains with what the ASTM standard says about that. Only could you jump in here? Do you know what
Sure.
the?
Sure, I can help you. I can answer that.
Okay.
So the basically the oil breakdown test is it's not one single test that you run. You run 5 breakdowns, and basically the final result that you get is it's an average value. Now the standards, both of them do have a statistical analysis there to determine if that value or that average value is valid. So basically, you don't want too much variation between the the 5 breakdowns, and so that your average is within a certain range. That is what the standard does, or the oil breakdown instruments do. They run that verification, and they verify that the value is within a certain range from the standard variation, and if it's within that range, then it means that the test is valid and it's a pass or a valid test. But it might be a low value. And if it is not, let's say that there's a lot of dispersion between the values or each of the breakdowns, then that means that the test it's preferable to run the test again, because the values are very different among them. So that's the valid or the pass that you see there, and that doesn't mean that your oil is it's good for your standard, and there are some standards, some expected values of the oil that you can see in the standards, but there might be some internal standards for certain voltage levels. So that's what you need to compare in the end.
Yeah, I've just pulled up the ASTM D1816 standard, and it says for a 1 millimeter gap setting, the range must be less than 120% of the mean of 5 breakdown voltages. And then for a 2 millimeter gap setting, the range must be less than 92% of the mean of 5 breakdown voltages. So I think it's clearly stated in the standard what the actual criteria is.
Mhm.
And the range is obviously the highest value minus the lowest value.
Yes. Thank you. Thank you.
Thanks, guys. Back over to James. Can we use bottle sampling for DGA, or does it have to be on a syringe for more accurate readings?
You definitely, if you're doing DGA, you want to use a syringe sample because that oil is never exposed to atmosphere, so you don't get loss of gas or contaminated gases entering the sample. So you always want to do DGA on a syringe sample. Now you can do a DGA sample on oil that comes from a bottle, but just recognize that at that point, you're testing the bottle and not the oil that came from the transformer, because it's going to be exposed to atmosphere. Some gases are going to escape, other contaminant gases may end up getting dissolved into the sample, and you won't get a representative result from the bottle. So always use a syringe sample if you're doing a DGA test.
All right, thanks, James. Volney, how many tests can be conducted on any given sample?
So the standards, both 877 and 1816, they do run 5 tests. And one thing to consider is that if you want to repeat the test, you didn't like the result, I've seen that you can repeat, or people will repeat the test on that same sample. But one thing that is happening is every time you break down the oil, that is carbonizing, so it's starting to create some contamination due to the test. That is one thing that could happen. The other one is every time you break down, you are probably burning or kind of removing moisture from the sample. So if you keep repeating and repeating tests, that probably the results are going to start changing drastically. 877, for example, has 2 methods, method A and B. One runs runs the 5 tests on the same sample, and the other method asks you to replace the oil for every of the 5 breakdowns. So just to be sure that you're getting the result. So I have not a specific answer for that, but there are things to consider there that might affect your results. So you don't want to run the test many times on the same sample.
Thanks, Volney. Over to James. What is the recommended material for the bottle? Aluminum, glass, or plastic, or anything else?
Okay. There's some controversy on the material for the sample bottle. Weidman's position is any of those are acceptable. Actually, we kind of prefer the plastic bottles just because they're a little bit easier to handle. Some labs require glass sampling containers. They're concerned that plastic will absorb moisture and contaminant results. And it is true that a plastic bottle will absorb a minimal amount of moisture, which is one of the reasons why you want to get it in the lab as quickly as you can. But our studies have shown that for up to 30 days, the amount of moisture that might get absorbed through the bottle wall itself into it really doesn't materially affect the moisture level results, which is the thing you're most concerned about. If that's stored in a high humidity environment for a long period of time, that little extra moisture that comes into the bottle might, in some cases, affect the dielectric breakdown voltage test result if you're doing that test. But in general, if it's properly handled and taken care of in a reasonable amount of time, there's really nothing wrong with using a plastic bottle. The glass bottles obviously are a little more impervious to absorption, but they're also heavier, so they cost a little bit more to ship, and they're prone to being broken if they get dropped or mishandled somewhere along the way. So each material has its pluses and minuses to it, but our position is we don't really have a strong preference for one over the other.
All right, thanks, James. And while I have you, this next question is also going to be for you. Could you please advise shipping restrictions on sending samples to the lab?
I'm not really sure what they're looking for there. The only thing that might be considered a restriction is if you're shipping an oil that's known to be PCB contaminated, that needs to be clearly labeled so that we don't test that sample before we take some our required protocols, so we don't contaminate other oil samples and test equipment in the lab. But as far as we don't really care what shipping company you use. We take from all the delivery companies out there. I suppose at some point there might be a limit to how many samples you can put in a container just from sheer weight of handling. But I'm not aware of any actual shipping restrictions because mineral oil is not really considered to be a toxic or dangerous chemical. It is considered toxic if it has PCBs in it, but other than that, I'm not aware of any restrictions on shipping.
All right, thanks for that, James. It looks like we've kind of blasted past our stop point here today, so we've run out of time for our Q&A session. We apologize if we didn't get to your question today live, but we will be working to follow up with you offline. As a reminder, a copy of these presentations, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.